Now it's okay. Okay, Control L. Yeah. Okay, so we now talk about we had some discussions on uh, the second law of thermodynamics, and of course leading up to this discussions on entropy. Now, uh, so the best manifestation of the second law would be when we talk about you know some engines, thermodynamics, thermodynamic engines, where uh, some heat is supplied to a system and then the system does work. Okay, so the basic idea that you absorb a heat from a hot substance, uh, which is called a reservoir at a high temperature, and you absorb that heat and then you go for an expansion, right? Now in that expansion you're displacing the volume, there's a increase in volume, and you perform some work against a constant pressure. And if you do that in a very slow manner, you'll be able to get a lot of work. That's a reversible work that you can get. But then the question is, uh, you can only do it once. All right. Now, for something to be sustainable, the engine should continuously work. All right. And then once you have come from high pressure to a lower pressure by virtue of the expansion, then you don't have a pressure head. So what you need to do is actually again you go back and build that pressure. All right. And then only you can go for another expansion. Uh, so to be able to do that, you have to have a series of processes, and which is not kind of straightforward, right? So this series of processes must involve certain thermodynamic steps or certain changes in the thermodynamic coordinates that it eventually gives you the maximum kind of work, right? And that's where it can go over a cycle, and then it can continue over multiple cycles to give you to perform for the system to perform work continuously over a prolonged period of time. So that's how the ideas of an engine, a thermodynamic engine, in a cyclic way that is evolved. So I think you guys are familiar with the Carnot engine, which is developed by the French scientist, engineer, you can say, Sadi Carnot. And this process involves several steps, which in an ideal way gives you or lays down the principles for maximum work output from a system. And so the basis is that you have a heat reservoir at a higher temperature, and the system um, uh, gets some heat transfer from the high temperature reservoir into it, and by virtue of that it performs some work, and at the end of half of it, it has to reject some heat to the surrounding. Okay, and it can go back to the earlier position, and thus it can work in a cyclic manner. So here two things are coming out, that how do you consume those steps of thermodynamic processes, where it can start from point 1 and then again through a series of steps you can go back to point 2. And here the simple formulation is that I think you guys know it, but we'll just simply go over it. So let's say here some amount of heat enters to the system, and by virtue of that the system goes for an isothermal expansion. And for all purposes, we'll consider the processes here to be reversible, so that there's no degradation of heat as such. And so through this, it goes through an isothermal expansion process. That means it starts from point A to point B, and since it is an isothermal process, the constant temperature has to be maintained in that. But in that process, what happens? You have an expansion from VA to about VB. Okay, and accordingly, the pressure gradually drops. So this is the step of isothermal expansion, right? Now at point B, uh, the system is expanded, but then at this point, it has to come and by virtue the temperature is the same, it's maintained here. Then it has come to uh, a lower temperature, and that it can do by an adiabatic expansion, right? So here the internal energy would change and the temperature would change, but then no heat enters and or goes out of the system. So from B to C is an adiabatic expansion. Now at this point, it has come to a lower temperature. That's the temperature of the sink. And this is where it can reject some heat, and that heat is rejected by virtue of a compression from point C to point B, point D, corresponding to the volumes VC, VD, and then this happens in the similar temp, in the same temperature. That's the lower temperature. Okay. Now again, from this lower temperature, it goes to the higher temperature, thus completing the cycle. So this process of D to A is an adiabatic compression. So in these four steps, what happens is that the system has come back to its original thermodynamic coordinates, that's point B, so that it can work once over again. Okay. So this is what constitutes a circle, and then for each of the steps, you should be able to calculate the work performed. Okay, yeah, for each of the steps, you should be able to calculate the work performed. This is NRTL and VB by VA. Likewise, we have reversible isothermal compression, that is NRTL and VD by VC. Right, this is the expansion and the compression. It's just say in just so that we can explain it, but then there's no change in the formula. The formula only corresponds to the final volumes and the initial volumes accordingly. Okay. Likewise, we have the work done through an adiabatic process, and since the adiabatic process would undergo changes in the temperature, and TH and TC are the temperature the high temperature. It's at the reservoir, and Tc is the temperature of the sink or the low temperature reservoir, or cold substance we call sometimes, and these two terms are pretty much the same. So like you've done, so the whole work is actually the area bounded by this thermodynamic coordinates A, B, C, and D, right? And so that you do by calculating the A small a, let's put this way, A, B, small b, and B, and then you add up B and small b, and then small c and C, and then you deduct C, and then say small d here, and then D, and then again D, small d, small a. So the total area minus this area from the compression strokes, and that's what eventually gives you the total work done. All right. So in this process, there is something called an efficiency, which is what we ordinarily want, that we should put some heat, and that heat should be able to convert all of it to work. Right, that's the ideal process that we can expect, so that there is nothing is lost. All right, but then turns out the importance of second law is that this process has to spare some heat to the surrounding, right, and eventually the useful work, which is the W is what we mean. We need to maximize W. That's depends on how good a cycle you can develop, so that the factor W can be maximized, but then it can never be more than one. Certainly it cannot be more than one, but it cannot be equal to one also. So you have to eventually reject some heat to be able to put in a cyclic mode. So turns out, I think there's no point going through the calculation, the whole thing. It's pretty easy. You guys might have done that. So this W is the algebraic sum of the heat the system gets and the heat the system loses. That's the algebraic sum, which is W. That's normalized by the total heat that you have taken. The system takes the initial stroke, and that turns out is a function of the temperatures between which the engine operates, and which turns out that 1 minus Tc by Th, that's the efficiency. So it turns out why this is extremely important for mechanical engineers to devise so many different kind of processes, different kind of cycles where you can optimize the term W or maximize the term W so that your engine becomes more and more efficient. All right, so that's okay, but then why do we as material scientists you know concerned, why are we concerned about that? Turns out that from this formula itself, it's very simple. If you how can you increase the efficiency of an engine from an outsider's point of view? If you have to look, it'll appear that if you're able to sort of use the engine between two temperatures which are extremely widely apart, that means Tc and Th have to be really, really apart. The difference between Tc and Th has to be large. All right? Because if the difference is large, then in an absolute scale, you'll see that Tc by Th would minimize. If that minimizes, 1 minus that would give you larger efficiency. All right? Now the question is, how small can you go in terms of the core reservoir temperature? Right? This is maybe a normal temperature, and atmospheric temperature is the least you could do, because if you want to go below atmospheric temperature just so that you could push this Tc low, then you're not talking about an engine anymore. You're talking about refrigeration, which is the complete different. It is a absolutely different cycle that of an engine, which actually requires energy to be put in the system so that it can cool the substance below the atmospheric temperature. So the least you could go is in the range of atmospheric temperatures, that is Tc. Right? You cannot go below that. So then how can you increase the efficiency of the engine? That you can do only by increasing Th. Right? That you can do only by operating an engine at a much higher temperature. Right? So that's where the materials engineers come in, because it is it's the mechanical engineer to decide what process to be taken and what temperature that the machine has to be operated so that the efficiency goes high. But then there's a limitation. Eventually it's an engine. It has to be built with parts, built with materials. And now if you're using an engine made of some materials at a certain temperature, you need to be able to assure that the material is not going to fail at that operation temperature of the engine. So materials development and efficiency of an engine, they go hand in hand. You cannot operate an engine at a higher temperature involving materials which are not suitable to be used at that temperature. Right? So they go hand in hand. So if the temperature of use is about 1000 degrees Celsius, then the materials engineer have to develop a material which, as a part of the component of the engine, has to sustain that thermomechanical load, and then it's not going to break down. Right? So that has come to the materials engineers, and has gone to the point that you can differentiate between the engines of exterior gas turbine engines vis-a-vis currently used gas turbine engines, vis-a-vis what are coming in terms of uh, the components that will be used in even much higher temperature gas turbine engines. So if you go back to the history of the development of turbine engines, you'll see that there's a lot of contribution of material scientists, starting from normal steel to other alloys to super alloys. Now, super alloys with ceramic coatings on top of it. All of these things have developed because people wanted to increase the temperature at which the engine can be operated. Right now, it has come to the point that super alloys and metals or metallic alloys have in some of the parts started peaking out. You still want to go for higher temperature, then it has to be the ceramics or ceramic matrix composites or fiber matrix composites made of ceramics and carbon, silicon carbide composites. They have to be operated, and they can be operated at much higher temperature, leading to higher efficiency. But then that's the challenge of the ceramists to develop materials which can do proper thermomechanical performance in those designated temperatures. So that's kind of, in a way, in terms of applications, important for us to understand that the higher you can operate an engine, the more efficient your engine is going to be. And for that, you need materials which can operate at high temperature without mechanical or thermal failure, right? Likewise, you can have other cycles. This the Carnot cycle that we talked about is kind of an idealistic way of series of processes which can go back and forth and derive work out of some heat source. Likewise, there are other cycles like the Otto cycle, which talks about the gasoline engine. I'm not trying to go too deep into that because that's for mechanical engineers to understand and take it forward. For us, it's just if you're just comfortable with the names of it and then what kind of processes go, I think we are fine with that. So this gasoline engines goes between two isocores and two adiabatic processes and two adiabatic temperatures, TH and TC. You can see it's curves in the PV diagram, much like you do it in a Carnot cycle. Interested people can refer to that. There's a lot of literature available, but I don't want to take it a lot further in the domain of our course. Okay. Like that, we have the diesel cycle developed by Rudolf Diesel. So interesting thing is that it can take air and then sort of do a spark and then and sort of fire it up. That's what happens in diesel vehicles. It works between an isobar and isocore, and again between two adiabatic temperatures. And the Rankine cycle works between two isobars. And then, of course, your available Stirling engine that works between two isocores and two isothermal processes. And all of these engines are much in the reckoning now. And some of these things are used in internal combustion engines and automobiles and vehicles and all those things. And sometimes you see that the Stirling cycle, they say it could be useful for very small equipments like the heart valves and then things like that. Depends on what the requirements are. So, but then knowledge of all of these cycles is definitely helpful. Okay, so if you want to at some point go for that later, then we'll you're free to sort of look it up in different sources. And then if you want to discuss something, we can privately discuss about that, but then not in the domain of these courses. Right now, so yeah, and now let me bring your attention to something which is in terms of entropy quite useful for us. Useful in the sense that in the materials point of view, can we understand something what's happening in a reversible or irreversible process and what its implications are with regards to entropy. All right. So here I have devised a problem. The problem is there in the book, but I made some other sort of graphics so that you can understand the thing. So here's a problem we're talking about, the freezing of lead. Lead, Pb, lead. Lead is a substance which actually melts at about 600 Kelvin, right? That's it's normal melting temperature, the equilibrium melting temperature. That's what we call equilibrium melting temperature, meaning we keep the pressure at 1 atmosphere, pressure is constant, and that's where it melts at about 600 Kelvin. Now, let's say there's something called a supercooled liquid, right? So above 600 Kelvin, lead will be in a liquid state, right? But then there'll be a situation where you can sort of bring the liquid pool of lead below 600 Kelvin, but you can keep still keep it in a liquid form. Okay, that we generally call as a supercooled liquid. You might have seen that glass is a supercooled liquid, which is not entirely correct. That's for another day. We'll discuss about that. That's glass is not a supercooled liquid. It's a separate thing altogether. Let's say you have a pool of say a liquid thing. You're abruptly putting it inside a refrigerator. All right. So you're trying to bring the temperature of the pool much lower, where it's not ordinarily in an equilibrium condition. So what I'm trying to say is that if by any chance you're bringing a pool of liquid lead to a temperature which is 590 Kelvin, right? Here in 590 Kelvin, the liquid lead should have been in a solid form. Okay, and since it is in a liquid state at a temperature lower than its normal melting temperature or freezing temperature, we call it a supercooled liquid lead. All right. Now the problem is the problem at hand is that if a mole of supercooled liquid lead at 590 Kelvin spontaneously freezes to a solid, all right, the same at 590 Kelvin, what's going to happen, right? Is there any production of entropy, or is there anything that's happening which is out of the ordinary? Right? That's the question. So if you go to the question, let's say what it says that calculate the entropy produced when a mole of supercooled liquid lead spontaneously freezes at 590 Kelvin and 1 atmosphere pressure. The equilibrium melting temperature of lead is at 600 Kelvin at 1 atmosphere. Of course, the enthalpy of melting of lead is given. It's 4810 joules per mole. Right? Now, of course, two other data are given, which is the specific heat of liquid lead and the specific heat of, at constant pressure, of course, of the solid lead. Right? So we need to sort of calculate or understand what's the meaning of production of entropy. Right? So normally what will happen is that if if there is a liquid lead at melting temperature, then you'll have to take some heat out of the system to make it solid lead at the same 600 Kelvin. So here to here is an isothermal process, and what's the heat that you have to take out from here? That's the latent heat of melting, latent to freezing, right? So if you take the latent heat from here and maintain the temperature, then you transform it to a solid substance. It could be lead, it could be tin, it could be something else. It's a generic process. At the melting temperature, there's no change in temperature, but then you have to take some heat out of the system so that the liquid substance becomes a solid substance. Likewise, you put in this process, you put the same amount of heat, the heat amounting to the latent heat of melting to at the melting temperature to the solid substance, then it transforms to the liquid. Like fairly reversible process. I think that's easy to understand. All right. Now, if you talk about this process that we talked about here, then what it says is that the 590 Kelvin, a liquid lead, 1 mole of that, it transforms to solid lead at 590. All right, this is given by the arrow in orange color. All right. But if you have to take the whole process in a reversible manner, right? What ideally would go, I mean, from A to D, what ideally would have been the process? The ideal process would have been that at 590 Kelvin, the liquid lead is heated from 590 to 600 Kelvin. It's a liquid, it'll take the liquid specific heat, and that'll be the dT. So Cp integrated over 590 to 600, that will give you the heat. For entropy, you'll have to calculate the Cp dT over T, right? Now you have a liquid lead heated to from 590 Kelvin to 600 Kelvin. Now that liquid lead heat is taken out from their system so that the liquid lead becomes solid lead. Now that solid lead has to be cooled from 600 Kelvin to 590 Kelvin so that it remains a solid again. So the process A to D can actually be carried out through the processes A to B, B to C, and C to D. All right. So if entropy is a state function, then no matter if you follow the process from A to D or follow the process from A to B to C to D, it should be constant. But then would it be constant? Question one. And what about enthalpy? Enthalpy is also a state function. So the enthalpy calculated for the process from A to D is going to be same as it is with A to B plus B to C plus C to D. Right? So these are the two things that we're going to do. We're trying to find out what's the change in entropy in the process from A to D and the other process as well. And we're trying to find out the enthalpy change of the process in the A to D process, which is a combination of A to B, B to C, and C to D process. All right. So let's do that. I've just solved out the example and see if you have any questions at the end of it. So the process is what we shall. I should have come to this slide again. So step 1 to B is 1 mole of supercooled liquid lead is heated reversibly from 590 to 600 Kelvin. And then step B to C, 1 mole of liquid lead is solidified at 600 Kelvin. The temperature, you know that the temperature doesn't change here. It's a melting temperature. And step C to D is 1 mole of solid lead is reversibly cooled from 600 Kelvin to 590 Kelvin. And the question is, the process and the question is A to D directly is 1 mole of supercooled liquid lead is irreversibly frozen at 590 Kelvin. So that's the irreversible process, and this is the series of steps is the reversible step. Right? There's something happening between here and here. Okay, does it actually refer to the production of entropy? We'll see that. Right. So if we have to calculate the entropy changes, we can do so by calculating the entropy change over the process A to D, that is del S A to D, which is a combination of del S A to B and del S B to C and then del S C to D, which is what is written here. And likewise, if you know that enthalpy is also a state function, then you can calculate the enthalpy change over the process A to D, which is again a combination of processes from del H's combined over A to B, B to C, and C to D. Right? And let's go and do that. So how do you do the calculation for entropy? Del S A to B, how do you calculate that? That simple formula. You have to have dq, the heat change over that, with temperature, normalized by temperature, which is simply written here dq over T integrated from this thermodynamic spaces A to B. And since we're talking about a temperature change here only, so it's integral 590 to 600 Cp dt by T, and Cp for, and this, since it is a liquid stage, we've got to be taking the specific constant pressure for liquid lead, which is what is provided to you with the question. So we do the calculation, it comes out to 0.514 joules per Kelvin. All right. So just think about the numbers. You know, it's not negative number; it's a positive number. And does it make sense? I think it makes sense because you're heating something from a lower temperature to higher temperature. That means at the higher temperature, the entropy is going to be slightly higher than the lower temperature here. And if that were then the del S of the process is going to be positive here, which is what is positive here. So I think it makes sense, seems correct. All right. Now, so from here to here we calculate. Now let's calculate from here to here. What is the del S through the melting? It's very important. Del S, what happens to the entropy change during the phase change, and how can we calculate that? I think we have at some point talked about it. The entropy change during a phase change is simply the latent heat normalized by the transformation temperature, which is what is here. It's QR by T del S, and this QR is heat transferred. And for this process that we're talking about, the heat transferred is nothing but the latent heat from solid to liquid, right? Solid to liquid. If it is solid to liquid, then it's going to be positive. From liquid to solid, it's going to be negative. Because if, for solid to liquid, you have to provide energy into the system so that it becomes liquid. From liquid to solid, you'll have to take the heat out of the system, then it's going to be negative. So solid to liquid here, I think there's a mistake. It should be liquid to solid, because that's we are going from here to here. So it's going to be L to S, and that's what is given is minus 4810 divided by the temperature, which is 600 Kelvin. That gives you minus 8.017, and this has to be minus. If you look at it, this has to be minus because this is liquid lead. All right, this is solid lead, and you are taking heat out of the system. When you're taking heat out of the system, the temperature, the heat change is negative, and therefore, if you normalize it with temperature, the entropy is also going to be negative. And of course, you know that solid substance would have comparatively lower absolute entropy as compared to this liquid counterpart of the same temperature. If that were so, then this minus this entropy is going to be lower minus higher. That's going to be a negative number. So it appears all right to us. All right. So likewise, what's the next step then? C to D. All right. If it is C to D, then what you're doing is you're trying to cool the solid lead from 600 Kelvin to 590 Kelvin. So which is what is written here, that del S C to D. There's a mistake here. It has to be C to D, not A to B. Right. And here it is correct, and that the integral over 600 to 590, and this is Cp of solid lead. That also is given in the question. You have, because by this time the lead has become a solid now. Now this is Cp dt by T integrated over 600 to 590, and that gives you the number minus 494, and it's a negative number because you know that you're starting from a higher temperature to a lower temperature. That means entropy is going to be decreasing in the system. And if entropy is decreasing in the system, the del S part has to be negative. So this also makes sense. Now, if we are taking from the reversible perspective, so del S A to D is going to be a combination of A to B to C, and C to D. Then when you put all of those things together, then you're getting del S A to D is minus 7.997. All right. Now, this is how we have figured out what's the reversible entropy of this transformation, the problem that's given. Okay. Now, let's look at from the heat point of view, the enthalpy point of view. All right. Now, so like we calculated the entropy change, we can calculate the enthalpy change as well. All right. Now, what's the enthalpy change is at the constant pressure, dq at constant pressure would be simply equivalent to dH, and dH, you know that you can simply integrate over Cp dt over the temperature ranges of your interest, and that gives you the enthalpy change. Now here, when you go from 590 Kelvin to 600 Kelvin of a liquid lead, you simply need to integrate Cp dt of liquid lead from 590 to 600, and that gives you 306 joules, and it's a positive number. And you see that you have to supply heat into the system. That means for liquid lead at 590 to 600, you have to supply heat, and that's the positive quantity. All right. So this is what the system is getting. Now, like that, like the entropy change over the phase transformation we talked about, we can also calculate. Well, you don't need to calculate straightforward. What's an enthalpy change over this transformation of liquid lead at 600 Kelvin to solid lead at 600 Kelvin? And since it's given it's 1 mole of the system that we're talking about, here it's simply the latent heat. It's minus 4810, which is negative because we are converting from lead, solid liquid lead to solid lead. So it's minus 4810 joules. Likewise, you go from the point thermodynamic coordinate C to D, which is cooling the solid lead from 600 Kelvin to 590 Kelvin. And the enthalpy change in the process is that this is getting cooled. That means the enthalpy change is going to be negative. That means you integrate it over 600 to 590 of Cp of lead solid dt. That gives you minus 294 joules. So enthalpy is also a state function. It doesn't really depend on the different processes that you follow. So even if you want to calculate del H over A to D, then it's a combination of all these 3 steps, which is what is given in minus 4799 joules. All right. Now, that's where we can do a contrast between these 2 things. Right. So, what has happened in the spontaneous process from A to D is that the enthalpy change of A to D, which is not going to change no matter, which is the same no matter how you take your process in a different way, in this 3-way or 1-way, it's the same thing. So what has happened in this process A to D is that all of this enthalpy change from A to B, B to C, C to D, that has happened spontaneously, immediately at the temperature 590 Kelvin. This is what we mean by the spontaneous process. This is what has happened in the process that was given in the question. So all the heat change has occurred at the temperature, at one temperature, is immediately, spontaneously at 590 Kelvin. So if we were to calculate the delta S of this spontaneous process, what we need to find out is this del H that we've figured out, that happening at 590 Kelvin, which is what is given here, minus 4799 joules transacted at the temperature 590 Kelvin, which is minus 8.314 joule per Kelvin. All right. On the contrary, we had calculated the entropy change over the processes of A to B, B to C, and C to D in a reversible way. Right? We have calculated, if you recall, you had calculated the Cp dt by T from this to this, and then taken out the dq by T, or the what's the entropy change of the reversible process of phase transformation from here to here. And then in a reversible manner, we cooled the solid lead from 600 Kelvin to 590 Kelvin, and then try to figure out what's the entropy change in that, which is the Cp dt by T integrating over 600 to 590 Kelvin, and we sort of added all of them together, and then we figured out that the reversible entropy change is minus 7.997. All right. The means what has happened is that the entropy change, if we started the process from 590 supercooled liquid to 590 solid lead, we should have gone then the reversible process by heating from 590 to 600, cooling the liquid lead to solid lead at 600 Kelvin, and again cooling the solid lead to at 600 to solid lead at 590. In this whole process, and if had it been conducted reversibly, the heat change or the entropy change would have been minus 7.99. it would have the situation, the process from A to D would have still gone to a lower entropy situation, but then the lower entropy, the entropy would have lowered by an amount 7.997. But the process being carried out spontaneously, we actually lowered the you know we went to a situation where the entropy change was minus 8.314 because of the spontaneity. So in this situation, if we were to calculate the production of entropy, what is the entropy, what is the additional entropy that is produced? That additional entropy is del S irreversible, right? So which is the spontaneous process minus the reversible process, right? If you do that, then you calculate that you are, by the spontaneous process, you are creating slightly higher entropy, which is 0.137. Okay, had you conducted the process reversible very slowly, okay, this much of entropy would not have produced. Okay, just because of the fact that you did it so fast, then you are producing this. So that's the extent to which this whole thing got degraded. And this, how would it manifest in this supercooled or no, solid um, lead? Because the fast freezing, it might so happen that the crystallinity in the solid lead at 590 might not be as great had as compared to, to the process where the system were carried out between A to B, B to C, C to D. You know, the quality of crystals that would have got from the solid lead at 590 Kelvin and the quality of structure or nanostructure, atomic structure, the way those atoms are there, when you conduct the process irreversibly, spontaneously from a 590 Kelvin supercooled liquid lead to a 590 Kelvin frozen solid lead, there could be differences, and that differences can be because of the production of entropy. All right. So we'll stop the deliberation of today here, and we'll take some questions that you might have. All right. So let me stop the recording, and then we'll take some questions. Okay. We'll stop the recording.